I respect this.
Also, they could have closed the door.
They could have closed the door.
What?
They could have
all
closed
open
the door.
ears.
They said at the beginning when they sent me up that whenever you hear.
Could you imagine? That would be kind of cool.
That would be kind
You
of
could
cool.
actually just like shut them off.
Yeah. Just like,
See, I can shut off all the background noise if there's a TV in front of me.
yeah. If I'm sufficiently distracted, if I'm doing homework, I'm not sufficiently distracted.
That's fair. I get in trouble at home because I can't, like, if the TV's just interesting. If it's something interesting, nothing else is going on. My mom will like try to talk to me and I'm like, huh?
What?
My brother will walk over and just pause the TV if he wants to talk to me. I have no freaking clue that anybody's talking.
Yeah, I get that way when I sometimes when I'm studying or doing homework, like someone had a full conversation last week for like 30 seconds and I wasn't registering anything because I was studying chemistry too. So they're like, hey.
Hey.
Pay attention.
Are you there?
Apparently I just look like I'm not, like I look like my eyes are glazed over. And I was like, you have a look on your face. Good to know.
I know that if I tried to talk to you right now, you would hear nothing.
Exactly. No, thank you. I'm just proactive about it.
Madden wants a gun. I've only got 2 pieces. So might as well just get rid of it.
Just drum machine.
Little do you all know.
No.
Remember how I talked about getting those samples for my research?
Oh.
The one problem.
Oops. See.
Are you gonna get the G okay?
What time is it again?
Basically our
We have
chemistry
class.
time.
What?
Basically our chemistry time.
Yeah.
It's from 11:30 to 1.
No, we have class here.
So, paper turned in.
Yeah,
So
she's
apologies for kind of the paper that I used. We ran out of paper. So, yeah.
It's heavy, yeah.
Also, here's some other homework too.
It is a heavy weighted paper.
Yeah, I know. That was the only thing that we had left. So, I was like, I'll have to use it.
My brain hurts.
You work, does your family work for Remax or work
My
with?
dad does. Yeah, no, he still does work for Remax. He also does a lot of contracting too. So he's
Oh,
kind of,
nice.
I think he's kind of wanting to switch a little bit for his job, but he does. He's done real estate for solid few years now.
Yeah. Do you know Susie?
Susie Clements?
Yeah.
Yeah. I think I've probably like come across her a few times.
Yeah, she was my real estate agent.
Really?
Yeah, she's pretty cool.
Yeah, I think my dad's worked with Susie. I know he's worked with a lot of people. I can't remember all of their names. It's been a while since I've actually been in the office and actually worked with people. But yeah, that's really cool.
Yeah.
I have two backup.
Yeah.
I feel like
Seriously.
What? I just see you guys
Like
pointing
this
at me.
one's done, I just have to and then
Yeah.
this one? I didn't draw it.
I
think that might be just exhaustion though.
I still have a decent knowledge.
But I did do good on that. I feel like
Actually, most of them are either chapter one, so those are like.
which is kind of exhausting.
That's a lot of
Either she's driving or not.
Is that?
Probably.
Oh, yeah.
So I Oh, you like.
You're really good golf though.
Damn. Okay, yeah, we should do that. But like,
And we live down.
I'll like,
Yeah. Like in the Tri-City.
All right, let's get to it. So last lecture. And so, right, all we have left is on Tuesday, we'll do our review. And then Thursday will be the final. And that's about it. And if you need to take it early, just let me know, and then you can, send the exam to the testing center. And then other than that, I think I owe you probably some grading, so I need to catch up on that. If you wanted to hound me down, so the problem is tomorrow I have a meeting like in Grants Pass, so I'll probably be in Grants Pass in the morning. But if you really, really, really wanted to track me down, you could maybe email me. Otherwise, I'll be on campus Monday, and then I should have your grading done, and then I'll hand it back Tuesday for sure. All right, and then my plan for today was just kind of to maybe go over some things we rushed on Tuesday, just kind of clean up any questions, and then of course I brought our fun demo. And so I was just kind of looking over the homework for a second, just so we could, again, figure out our highlights, what we need to take away from the chapter. And so I was going through it, and I wanted to go over this again, just because I felt like we rushed it. And so let's look at the difference again between the alpha and the beta glucose and what that means, and a few more details about that. Oops. And so, right, we had gone over on Tuesday just that our starches are our polymers of sugar. And then I wanted to point out a few more things. So we had just gone over this on Tuesday, and we had mentioned, right, the difference between the alpha and the beta form. But there are probably a few more things I should have pointed out. So for example, let's start off with, well, what is the name of this carbon here? And so this is an important position in sugars. And so this is a better form here, so we can kind of see what happens with this carbon. So that's a carbon that we're looking at. And so this is what's called the anomeric carbon. So that one here, where we can introduce some stereochemistry. And what's relevant about it, why it's called the anomeric carbon, and why we look at it, why we look at the stereochemistry, is because it's pretty reactive, again, comparatively in our sugar molecule. And so it's right next to our oxygen. And so just looking at resonance structures, so we're not breaking the connectivity, we're just moving our electrons around to make some resonance structures. And so that's what they're showing here, moving the electrons off of the oxygen to this bond here, so it's shown on this next figure. And so that makes this carbon reactive as well, and can explain some of the stereochemistry changing that happens. And so for instance, here are just some examples of substitutions that can happen at that anomeric carbon. Again, right, just identify it. It's right next to the oxygen. And just kind of compare, right, it doesn't matter. So this is a 6-membered sugar versus a 5-membered sugar, but either way, it's always next to that oxygen there in that position. And again, takeaway, it's susceptible to nucleophilic attack, right? So basically something with electrons is going to attack this carbon, and then, right, those electrons want to go back to oxygen, so that's why it wants to make a bond there. And then I just wanted to re-show you, since sugars can be confusing, and they're often shown in different kind of forms. And so this form is kind of like our 3D chair configuration of our rings that we've kind of seen before, like in cyclohexane. I think we drew that structure. So this would be kind of the analogous structure here. And so we're just pointing out, right, our alpha. And so they're both pointing down. So, right, these OHs are what we're looking at. So our anomeric one compared to this one over here across. So both pointing down. So in this one, they're shown in a different configuration. So now using the dashes, let's zoom in just a hair. So now this is kind of more flat, but then we can still see that they're both pointing down from the dash notation, right? So they're both dashed there. So it depends on how it's drawn and kind of what you see. And so this is another form. I forget what the name of this is called, because sugars have a bunch of different projections that they can be in. I'm not a sugar chemist, as you can probably tell. And so again, they're both pointing down in this configuration. And then if we compare that with our beta, so now this one is up. So right now they're opposite. So we can compare, and then again, compare the stereochemistry. So they were the same, right, both dashed, and now they're opposite, right? One is up, one is down in this configuration, and then same thing on this one. So now it's up versus the down. So hopefully that kind of helps with writing, right, our alpha versus beta sugars. And again, we're just focusing on this anomeric carbon when we look at that. So I think that's kind of the rundown of sugars. Do we have other questions on the sugars? And then we kind of went over this in class. So, right, we had mentioned that these were diastereomers. And so that goes along with this. So, right, they're different. They just have, so they're optical isomers. So yes, only different at this carbon. And right, so they're not enantiomers, but they're rather the diastereomers, where they have, it's not a complete mirror image. So right, a true enantiomer is a mirror image, while a diastereomer might have one stereocenter flipped, right? So that's what we're seeing here, is we only have this stereocenter different at the 4th carbon, and the rest are the same. So that makes it a diastereomer. So that was what we needed to take away from that. And then for 3 here, all we really need to say is this is like a 6-membered sugar versus a 5-membered sugar. 5 versus 6, so just kind of seeing that. All right, I think that's good for sugars, or at least I feel better about sugars. And so let's look at some other stuff. So let's go back and kind of clean up our DNA section as well a little bit. And so I posted a paper, which now I lost. Here it is. So I posted this on Blackboard just because I liked it for a couple of reasons. And so I just wanted to re-emphasize a few things, and then we can talk about DNA replication more, which, again, you probably got a better feel from biology. And so I want to just clarify what we mean by the 5' versus 3' end, right? So we had kind of mentioned that DNA codes, and this 5' to 3', and then the opposite is 3 to 5. Well, let's just analyze that a little deeper. And this is why I like this paper, because it labels the carbon, and it's showing, so right on this end, our 5' strand, it's connected to the 5 carbon, so that's where the 5 comes from. And then it has the numbers, so your 1 starts to the right of the oxygen, and then of course just goes around like we've numbered normally. And so there's our 5', and then at the end, what it means by our 3' end is we have our hydroxide end on our 3rd carbon, right? 1, 2, 3. And then remember, they're kind of like mirror images and opposites. And so kind of notice, right, the sugar is upside down, basically, from this end to that end. And so that's why this is the 3' end, and it's kind of right backwards when we write out our corresponding base pairs. And so like you all kind of got a sense, right, I'm not as familiar with our start and stop codons. What we want to take away from our class is just the pairs that they're paired with, right? And especially I was emphasizing the 2 hydrogen bonds versus the 3 hydrogen bonds, aka that's why they pair. And so let's look at the replication, and then we'll probably watch a video because they explain it a little better. And so we have, right, our DNA strand that's shown here, so our original DNA in black. And then, of course, now I blanked on the enzyme that's used to cut the DNA. But, right, it cuts it. Man, none of you chimed in. Help me out here, biologists.
It's like ribose or something.
I think it's literally
Or ribose.
zipper
Oh,
case or
yes.
something like that. It's
Something
literally
like
with like zipper.
Zipper. Well, so much for biology. No. I know the video will say it, but yeah, some sort of enzyme comes and then it unzips it, right? And so this is where the difference in synthesis comes in. So if we have, right, so let's say this was our 5' end, and then this is our 3'. And then so when the DNA goes to make it, it can only go in the 5' to 3' direction, though. And again, we'll watch the video and he'll explain it better. But basically, so on our leading strand, so this one can just be synthesized normally, right? So opposite, so this is 3', so then we can go 5' to 3' just normally. But then this lagging strand is a little weirder. And let's just watch the video, so you don't have to.
Helicase.
Yeah. See, I don't know my enzymes.
That was over a year ago for me. Something ace.
They both want to unzip your genes. Helicase is marvelous, unwinding the double helix at breakneck speed, slicing open those loose hydrogen bonds between the base pairs. The point where the splitting starts is known as the replication fork. It has a top strand called the leading strand, or the good guy strand as I call it, and another bottom strand called the lagging strand, which I like to call the scumbag strand, because it is a pain in the butt to deal with. These unbound sections can now be used as templates to create 2 complementary DNA strands, but remember, the 2 strands go in opposite directions in terms of their chemical structure, which means that making a new DNA strand for the leading strand is going to be much, much easier than for the lagging strand. For the leading, good guy strand, an enzyme called DNA polymerase just adds matching nucleotides onto the main stem all the way down the molecule. But before it could do that, it needs a selection of nucleotides that fill in the section that's just been unzipped. To get started at the very beginning of the DNA molecule, DNA polymerase needs a bit of a primer, just a little thing for it to hook onto so that it can start building the new DNA chain. And for that little primer, you can thank the enzyme RNA primase. The leading strand only needs this RNA primer once at the very beginning, then DNA polymerase is all, I got this, and it just follows the unzipping, adding new nucleotides to the chain continuously all the way down the molecule. Copying the lagging or scumbag strand is, well, it's a frickin' scumbag. This is because DNA polymerase can only copy strands in the 5', 3' direction, and the lagging strand is 3', 5'. So DNA polymerase can only add new nucleotides to the free 3' end of a primer, so maybe the real scumbag here is the DNA polymerase. Since the lagging strand runs in the opposite direction, it has to be copied in a series of segments. And here that awesome little enzyme, RNA primase, does its thing again, laying down an occasional short little RNA primer that gives the DNA polymerase a starting point to then work backwards along the strand. This is done in a ton of individual segments, each 1,000 to 2,000 base pairs long, each starting with an RNA primer. These are called Okazaki fragments, after the couple of married scientists who discovered this step in the process in the 1960s. And thank goodness they were married so that we could just call them Okazaki fragments instead of Okazaki-someone fragments. These allow the strands to be synthesized in short bursts, and then another kind of DNA polymerase has to go back over and replace all of those RNA primers, and then the little fragments gets joined up by a final enzyme called DNA ligase. And that is why I say that the lagging strand is such a scumbag. DNA replication gets it wrong about 1 in every 10 billion.
All right, so I think that's kind of a better explanation. And again, I just wanted to kind of show why we have all those fragments, and again, why it has to be synthesized weirdly since it's from that 5' to 3'. So that's posted so you can kind of read through it and look at it. And so then, you know, the most I would make you do in an exam is like maybe pair up some of these to their amino acids, kind of based off of that. But again, just kind of a very simple approach to DNA.
We're not gonna have any problem where we have to draw like protein structure, where you give us like glycine and then like 3 other proteins.
Oh, yeah, so we'll have to do kind of like the last example that we did on, yeah, so there'll probably be something like this, or I think how it's currently written on your exam is that I give some structure and then I say, look at it, see if there are errors in it, you know, kind of highlight the errors, that sort of problem. But yeah, same basic thing of like, can you draw this chained? I think that was on your homework too, so I don't know if you all want to practice that. Maybe we need, yeah, let's look at the homework. And so let's just try this simple one. So just see if we can draw this dipeptide. And then we can always draw some more. How's our drawing going? Maybe more time. So if you compare your structures, so the first thing I did was cheat and draw out, right, our just generic template. And so now I can fill it in. So I refer to my compound chem sheet now. So PHE is phenylalanine, and now I can put in the appropriate R group. So that helps me. So I'll rewrite this, right, CH. And now our phenyl group here, so I just kind of abbreviated. Then our amide bond. Now we start asp or asparagine, or sorry, aspartic acid. Okay. And so again, write R group. So draw it, so CH. Now my new R group. So depending on its protonated or deprotonated form. So this could be a negative charge or hydrogen, and then finish off our structure there. And then what if we want to draw the opposite, right? What if we had been given the dipeptide asp fen? What would that look like? Yeah, so switch around the R groups. That's one easy way to look at it.
Or I just picture the whole thing.
So I'll draw it. So now our amine, right, our aspartic acid has our amine group on it, so they just kind of flip a little. Oops, lost my hydrogen, my amide bond formation. And then now phenyl, and then of course the phenylalanine then has the carboxylic acid group. So let's see what else is good. Oh, we should mention this. I think I forgot to talk about it. So what's a saturated fatty acid? Think back to what does it mean when we say we have a saturated hydrocarbon?
It's only got single bonds between all the carbon chains.
Yeah, so single bonds, so refers to saturation of hydrogens, right? So, you know, some sort of fatty acid then, just a long straight chain, you know, blah. And then, of course, just our carboxylic acid at the end for our saturated fat. And then unsaturated, you know, doesn't matter too much. Just want to draw in some double bonds. You could actually look some up. Or, again, just note, right, it's any sort of double bonds in there. And so let's just look at this so we're all on the same page. So again, we're just taking a simplified approach. So see if you can do this real quick. So what would be the complementary strain of this section? So we're not trying to decode it into proteins right now. So what is A paired with? T and then C. So then we have G, G, and then A, and then keep going. So G, C, T, C, perfect, 5 prime. And so this would be one way to write it, and then you could also just write it right in the 5 prime direction. So just kind of rewriting it, right, CTC. If we were reading it, how it would synthesize it, and GAG, GT. See, this is the problem with chemists, and you guys would criticize us, right? That we have an odd, it's like not coding for anything, since, anyways, right? We have 3, 3, and 2, so that's what happens when you get chemists involved. So, again, we're just taking our simplified approach.
So on the test, do you want us to do that flip it around to the 5 first?
Either way, yeah, because I mean, me personally, I kind of understand it, the 3 prime, 5 prime better. I just know the key writes it this way as well. But yeah, I'd be open to either, since it's the same thing. Let's see, anything else? Any other questions before I probably skip over to our demo? All right, so let's try our demo then. So we have our demo. And so let's just write out what we have. So we have an aqueous solution of our hexamethyl diamine, so our hexane diamine solution. So 1, 2, 3, 4, 5, 6. And then it has 2 nitrogens on the end. And then we're going to react it with adipyl chloride, which I'll write out the structure for it. And so adipyl chloride is just a fancy name for this thing. So 1, 2, 3, 4, 5, 6 again. Oh. Hang on. 1, 2, 3, 4, 5, 6. Okay, double checking my carbons. So it also has 6 carbons in there. And then instead of a carboxylic acid group, it's a chlorine. I think that makes it a little bit more reactive. And this is also a cleaner reagent from my understanding. And so then we're going to do a condensation reaction. So our nitrogen, right, has lone pairs. We've learned that these carbonyls tend to be susceptible to nucleophilic attack here. And so that's what's going to happen is we'll make our bond. And then once this reforms, we're going to lose hydrochloric acid instead. So right, we'll lose 1 hydrogen from our nitrogen, a chlorine here. And so right, normally we lose an OH and make water, but in this case, since we're using our adipo chloride, we'll make a little bit of HCl gas. All right, so let's do the demo here.
Sorry, when do molecules form in this?
Oh, so then, yeah. So then we'll make nylon 6,6 here. And so it's called 6,6 since both of these have 6-membered carbons. All right, so we'll make our 1, 2, 3, 4, 5, 6. And then with our nitrogen, so 1, 2, 3, 4, 5, 6. And then, right, repeating. Oops. Yeah, and you can, if you make other nylons, the name changes depending how many carbons you have.
Like how many carbons each polymer has?
Yeah, like each, because instead of like adipo chloride, you could have used like I think it's called sebaceous chloride, which is 8 carbons instead of 6, so it just depends what you're using. All right, so let's do our nylon demo. Where's my other glove? So we'll start off, we have 2 dry, clean beakers. And so first we're going to put our aqueous solution in. So this is, again, 5% aqueous solution of our hexamethyl, or hexane diamine, I'll just call it. So the hexane diamine is a solid white powder thing, and then I just put it in solution. We need about 8 mils of this.
Is it dissolved in water or some other solvent?
Yeah, it's in water, so yeah, 5% in water there. And then I'm just going to add some sodium hydroxide, so a little base catalyze. So that's 1 beaker. And then I'm going to mix, so we have, oops, that's not that one, our adipo chloride. Kept in here since it's a little nasty. Not making enough. Oh, no. Okay,
All
hopefully.
this stuff that's in the container.
It's just absorb, yeah, like it helps absorb it in case it were to break and spill. But I hope I didn't mess with my reactor. We'll see if it still works. I got like Zorb stuff in there.
You have the same speaker.
I'm supposed to layer, so I'm going to take about half a ml of the alkyl chloride, and then we're going to dilute it in some cyclohexane, just an organic, 8 mils of it. And then, now I'm going to layer it carefully. Oh, so if I layer it, so it's kind of hard to see. I'll walk around with it, but right, so I'm adding it to our aqueous layer, and I'm just putting the organic on top, and I'll walk around. But it's starting to make this film, and that's our polymer. Let me just add the rest of our alkyl chloride. It's kind of hard to tell since it's like a milky film. All right, so now I'll walk around with it. So yeah, you can kind of tell on the video now. You can see how it has 2 layers. It's easier. Oops, trip over my camera. That's right, we got 2 layers, and you can see the weird film. So the weird film, that's the nylon forming. Walk around. And we've got the weird film.
Let's make something out of it.
We almost can.
We need a little bit more probably.
Film. Right, you can see. Kind of weird. Yeah, looks kind of gross. Yeah, let's see this. And so now that here's the fun part. So now that we have our layers, we can pull it out. So I can just grab it. And so now we can just kind of pull it out and spin it. And it'll just kind of keep going as long as,
As long as it keeps reacting.
yeah, as long as there's material in there. Yeah, so if you want me to take another tour around the room.
That's what I was thinking.
So we can touch it after I wash it. So I can go wash it, you know, while you are quizzing, and then we can pass it around. Just like yeah. Just kind of keeps going. So, right, this is our nylon then. So that's kind of what they do in industry. I'm not sure. Yeah. Looks like a huge booger or something really gross. But yeah, they just, you know, make nylon or other, what are those new synthetic fibers, like Vicos? Lightning and everything. But yeah, any synthetic fibers, a lot of them are polymers. That's nice. All right, I will go wash it, and then we can touch it. Is there anything else that we should kind of cover for lecture topics? I feel like we hit the highlights of at least this chapter. Sorry? Yeah. Well, we hit the highlights. All right. Sounds like we're okay. Let me hand out your quiz, and then I will wash our nylon.
This
is just like the rough sketch, and she said I can make it into now, and then when she does it, like, when I come in tomorrow, I look at it on the tablet, and then when she puts all the stencils, then I can make it. I did think it was kind of last minute, and she only sends out a rough draft of the thing, because she doesn't want to send out full ones. She only does original stuff, but she won't do